Welcome to this module. We are looking at the digital measurement, reporting, and verification technology stack. People often call this dMRV. dMRV replaces manual steps with technology. It combines satellite imagery, artificial intelligence, IoT sensors, and distributed ledger records. These tools collect, process, and verify data with far less manual handling. However, each layer of this stack has real strengths. Each layer also has documented failure modes. A climate consultant must understand both sides. You need to know how the tools work. You also need to know how they fail. This knowledge helps you build strong systems. It helps you avoid costly mistakes. In this module, we will walk through the 5 main layers of the dMRV stack. We will look at the benefits and the risks for each one. The first layer is IoT sensors and metering. The Internet of Things means physical devices with sensors and software. These devices connect and share data over a network. In dMRV, these devices provide continuous, high-frequency data streams. They replace periodic manual sampling. A clear example is Gold Standard's metered cookstove monitoring. In this approach, sensors on stoves record actual usage. Emission reductions are computed from measured cooking events. They are not estimated from surveys. This shows the difference between an estimated and a metered indicator. A metered indicator uses direct measurement. An estimated indicator uses assumptions. Yet, IoT sensors face real engineering problems. Sensor drift happens when a sensor's baseline reading shifts over time. This leads to inaccurate measurements. Calibration loss makes this worse. The sensor no longer maps its signals to the correct physical value. IoT devices also depend on local power supplies and network connectivity. If a battery dies, the sensor stops working. If a cellular connection drops, data cannot transmit. These events create data gaps. You must account for these gaps during verification. Verification is the independent check of project data. Verifiers will look for missing time periods. They will ask why data is absent. You need a plan to manage these gaps. You might need backup batteries or local data storage. The system should store data safely until the network returns. As a consultant, you must design for these failures. You cannot assume the technology will always work perfectly. You must build resilience into the monitoring plan. This ensures the data remains reliable even when hardware fails. The second layer is remote sensing. This means acquiring images and data from satellites or aircraft. Remote sensing provides broad spatial coverage. It is very effective for monitoring land use and forestry. It also helps with some agricultural parameters. However, optical satellite monitoring has limits. Optical sensors rely on visible and infrared light. Cloud cover obscures the ground. This creates temporal gaps in the data record. Remote sensing is also constrained by resolution and revisit limits. Resolution is the smallest object the sensor can see on the ground. Revisit time is how often the satellite passes over the same place. A high-resolution sensor might have a low revisit time. You get very detailed images, but only rarely. A satellite with daily revisits might only offer coarse resolution. Consultants must balance these trade-offs when writing a monitoring plan. You often need to combine different data sources. You might combine optical data with radar. Radar can penetrate clouds, but it has its own challenges. Radar data can be hard to interpret. You need skilled analysts to understand the images. You must match the sensor type to the project boundary. The boundary is the physical or operational limit of the project. If you monitor a small forest, coarse resolution will not work. You need high resolution to see individual trees. If you monitor a huge landscape, high resolution might provide too much data. You need a practical way to process it all. Choosing the right remote sensing strategy is a key consultant skill. The third layer consists of automated pipelines and APIs. An API is an application programming interface. It is a set of rules that lets different software applications talk to each other. In a digital workflow, data moves through 6 steps. These steps are data capture, standardization, quality control, calculation, independent verification, and registry issuance. Data moves through these steps without manual re-entry. APIs make this movement possible. The main failure mode here is silent failure. A silent failure happens when a data pipeline breaks. The system does not raise an alert. Data stops flowing. Calculations run on old, stale inputs. Records are skipped entirely. There is no error message. Because there is no manual handling, no human notices the gap. No one sees the problem until the verification stage. By then, the missing data may be lost forever, or the project may have reported incorrect figures for months. This creates a huge problem for the project developer. It damages trust with the verifier. Robust pipeline design prevents this. You need automated monitoring and alerting systems. These systems must flag any interruption in the expected data flow. They must send a warning when data stops arriving. They must check that calculations use fresh data. As a consultant, you must ask about these alerts. You must ensure the pipeline has health checks. A digital system is only good if it actually works. The fourth layer is registries and distributed ledger records. A distributed ledger is a database shared across multiple sites or institutions. Blockchain is a common type of distributed ledger. These systems record carbon credit issuance and transfers. The main strength of a distributed ledger is immutability. Once a transaction is recorded, it cannot be altered or deleted. This provides a tamper-proof history of carbon assets. However, there is a critical failure mode to remember. An immutable record of a wrong number is still wrong. If a drifted sensor feeds an incorrect figure into the ledger will preserve that error forever. The ledger only promises that the record cannot be changed. It says nothing about whether the number was right when it went in. Reversing an error on a distributed ledger is very difficult. It often requires complex compensating transactions. You cannot just do a simple database edit. This makes pre-issuance data validation essential. The system must check the data before it writes it to the ledger. It must reject numbers that fall outside expected ranges. It must flag data that looks unusual. The baseline is the reference point for measuring emission reductions. The system must ensure the data matches the baseline logic. If wrong data enters the ledger, the carbon credits are flawed. Buyers may reject them. The project loses credibility. A consultant must design logic checks. These checks must run before the immutability feature locks the data in place. The fifth layer is digital audit logging. Continuous audit logs are time-stamped, read-only records. They record every action taken within a system. This includes data ingestion and calculation adjustments. dMRV maintains these continuous audit logs. This means verifiers review structured data. They do not have to reconstruct scattered records from spreadsheets and emails. An independent verifier can trace any issued credit back through the system. They can follow the trail through the calculation engine. They can check the quality control steps. They can even look at the original sensor reading. The World Bank's Carbon Markets Infrastructure Working Group produced a technical guidance note on standardizing digital MRV. This note includes evaluation criteria for assessing system performance. It helps identify where digitization adds value. A robust audit log is central to meeting those criteria. Major programs increasingly accept and encourage digital data pipelines. Vera, Gold Standard, and ACR are moving in this direction. This is especially true for removals. The claimed benefits of dMRV include lower transaction costs. It should also provide better data accuracy. It aims for faster and more credible issuance at scale. But as a consultant, you must evaluate the system. You must not just believe the marketing claims. You must assess whether the IoT sensors have a documented calibration schedule. You must check if the remote sensing strategy accounts for cloud cover. You must see if the APIs have automated heartbeat monitoring to prevent silent failures. You must ensure the ledger has logic checks before applying immutability. Your role is to protect the integrity of the carbon credit. You must not just automate the production of a number. To finish this module, you need to complete a practical task. Produce a dMRV technology risk assessment for a proposed project. Map each technology layer to its documented failure modes. Start with the IoT sensors. Then cover remote sensing, automated pipelines, and distributed ledgers. For each layer, specify the mitigation controls required for verification. Explain how you will prevent sensor drift. Explain how you will handle cloud cover. Show how you will detect silent pipeline failures. Describe the logic checks you will use before the ledger locks the data. This assessment shows you understand the real risks of digital systems. It proves you can build a dMRV system that verifiers can trust.